like to start with a complete new topic because we discussed quite intense about transport, but anyway, I would like to recap the last 4 transport lectures a little bit. So what do you remember from the last 4 transport lectures? So this was a very important topic and we finished it now, and what do you remember from the last 4 lectures? Maybe you can tell me something. Okay, is everything correct what you said? But I would ask you, so you said we can make a force balance, we can derive Navier-Stokes equation, and then we can put some into it, but I would have it a little bit more in a frame. So everything is correct, but can you frame a little bit more? We kind of put more order in the last 4 lectures. So who can tell me something about this? You?
We started from like what is aerosol, and how the aerosol is used and its movements, and we derived like the equations for its movement.
Yeah, that's correct, but you're again very fast, very specific in the examples. But we started very generic, and then we specified. So how does this work? What was the meaning? Yeah? Yeah?
We first start with how particles settle, and we...
This was again a specific example. But what was the main question of the 4 lectures, the last 4 lectures, the really main question?
How particles transport.
How they move, right? So how do we answer this question? That's already specific. Which equation? Yeah, very good. Exactly. Very good. And this is the answer I want to hear, okay? So everything you said is correct, but I want to see that you understand this procedure. The general question was, how do particles move? And the answer is, we can describe the movement by the Navier-Stokes equation. Then you can tell me, what are the 4 parts of the Navier-Stokes equation? Yeah? Yeah. Yeah, perfect. Transient plus convection equals external forces plus diffusion. And then we dived into it, and then we had 4 lectures where we looked at how particles settle, sand falls down, droplets in the air, what changed for the equation. We looked at thermophoresis, what changed at the equation, and what is thermophoresis. We looked at diffusion, what changed for the equation, what is diffusion, how do particles diffuse, and these things. And this is really one of the main takeaway of this lecture, right? So, and this is finished now, as you see here. So this was a really big part. And now we go into something completely new, and this is light scattering. And light scattering is an extremely cool topic, but I don't know much about it, unfortunately, because it's an extremely complicated topic. And I also don't know if other classes really cover this topic or to which depth, because we also have the classes from Thomas Justel, right, where we talk a lot about light and illumination, and we will have maybe a little bit overlap, but I also talked to him, so maybe we will have, or I hope you get something from this class or see the aerosol perspective here. So just to talk again about what you should learn in the lecture. So as you know, I want you to get a good overview about aerosol technology, and there I want to show you how particles interact with light and why this is important that particles interact with light. Actually, you could already in the first lecture, we talked about planetary boundaries, right? Did you remember? What was the relation of planetary boundaries to aerosol technology? Huh? Radius. What were the planetary boundaries, the concept of the planetary boundaries? Yeah, so just to let me repeat, so planetary boundary is a concept that we have boundaries and we not only have climate change is one of the fields, and if we cross a boundary, we will get really, really troubles because it's kind of kipping points, right, which we read. And aerosol concentration in the atmosphere is one of these 7 or 8 planetary boundaries. And you mentioned correct, the aerosol concentration not only recently, but since industrialization doubles the amount of aerosols, and this has an impact. We will talk today again about these impacts of aerosols in the atmosphere. And you also mentioned something, and this is that it's not so easy to determine the boundary for aerosol concentration. And this has to do with how to measure. And optics is a very powerful tool, and this is one of the ideas to set a value. Because for climate change, the value is determined in CO2, right? The amount of CO2 or CO2 equivalent. And something similar we would need for aerosols, and the approach here is to use the interaction with light to get an idea of the concentration, right? So here it's really about measuring and about valuable measuring. So it's important to understand the basics of how particles interact with light. And as I mentioned, also we want to talk a little bit more about aerosols in the atmosphere. We can relate a lot to technical applications, but this is then mainly measurement techniques. Okay, so when we talk about optics, we talk a lot about measurement techniques, and there is a reason why the optical ones are very powerful. And here, as I also said, it has to do a lot with smoke, and I just have to switch off the light and take care that I don't lose the camera. So again, I show you the picture of my brother-in-law, and I would like to take a look at this picture and tell me what you see there, what could be related to the lecture today or the topic of the lecture. Because again, we see something you maybe already noticed or not, and this will be fundamental to understand the content for today. So what do you see on this picture which has to do with the topic, yeah?
Part of the picture where the smoke is, the background is unclear.
Yeah, very, very good. So where the smoke is, the background is unclear. That's a very good point because no student explained it in this way, but this is something we will discuss later. So we will lose light, right? So that's a very good point. What else? What else do you see if you look at the smoke? Do you see any difference in the smoke? Yeah?
I think the difference in the smoke, in transparency of the smoke,
Yeah.
it depends on the concentration of nanoparticles or particles in that.
It depends on the concentration, that's right. So because we have the same size particles here, we don't see them because the concentration is lower. It also depends on the size. We will talk about this. But what else do you see? If you look at the smoke from the cigarette and the smoke out of it, you should know.
I think one point is that the speed of smoke is faster when it comes out of mouth, but when the smoke is closer to mouth is much clearer, and the speed goes down and spread in the air.
Yeah, that's correct. That's a very good observation, and this has again to do with transport. Okay, so you see that it's like the droplet coming out. It's deaccelerating, right? So the smoke comes out very fast, and it's deaccelerated. But this would be transport. Just take a look at the smoke and describe me what you see. What do you observe which could be related to the title of this lecture? Yeah. Mm-hmm.
Different contrast. For example, the part you have the black background,
Mm-hmm. Mm-hmm. Yeah, completely right. So the contrast and how to look through. And this is something we will discuss in the lecture. We will also have a small example. But what else? Look at the smoke of the cigarette and from the mouth. And there is a very big difference between both.
It's about the laminarity of the flow.
Yeah, but this is transport. You're right, it is, but I don't talk about transport here. It's about, as she mentioned, scattering. So what do you see when you look at scattering? Yeah? So you can see some light beams. Good. What do you see? It's correct, but there's something much, much more simple and clear to see.
For me at least, it looks like the smoke out of the cigarette is brighter.
Not only brighter, it has a different. Yeah? Yeah. The concentration is higher, it's more sharp, but there's also something, it's correct what you say, more bright, but put it into perspective. Yeah? Is higher concentrated? Okay. Okay, we will talk about this. We will see if this works. But try to describe, you said more bright.
It's white.
Yeah, it's white. And the smoke from the cigarette is white? It's gray. And if you take a closer look, it's blue. Okay? So it's bluish. If you look at somebody, and even here, if you take a look, it's not a perfect picture, but smoke from a cigarette is bluish. And if you observe somebody smoking, you can directly see it. So the question is why the smoke from the cigarette is blue and the smoke out of the mouth is white. And this is something I really would like to discuss with you. And therefore we have to talk about some basic things. And one thing is, I mean, all of you know this, ASML. Where did we already see this? Who remembers? I mean, there are thousands of these pictures, but there's a reason why I took it from ASML. What was ASML? There we already talked about wavelengths and the importance of wavelengths. Was related to thermophoresis. What was the application of thermophoresis? Or one application? Yeah? Yeah, that's a very good one, but is there this diagram important for? Light glass. The fiber optics. But is this diagram important? Is ASML an important company when it comes to light fiber or or optical fibers?
I think it was related to electronic chips.
Yeah. So when we talked about electronic chips, right, then we looked at this diagram and we need very short wavelengths. This is what we need because the wavelengths basically determines the small structure you can do. And now here we take a look at the visible part. So for what we're talking today, the visible part is important. And what I would like, so I first make some basic definitions. And this is that light is defined as visible electromagnetic radiation having a wavelength lambda. What is the wavelength of visible light, roughly? Yeah, 400 to 700, 400 to 800, something like this. Okay, 400 to 700 nanometer, and a frequency f of 4 to the power 14 till 8 to the power 14. So it's really, really fast. Which wavelength has the high frequency? Which wavelength has the low frequency? So these numbers are somehow connected. How are they connected?
The lower wavelength has the higher frequency?
Yeah, the lower wavelength has the higher frequency, and this is why we generally can say they are connected like this. C is lambda times f, so the wavelength times the frequency is the speed of light in vacuum, and this is 310 to the power 8 meter per second. Good. So then we need another one which we need to define, and this is the ratio of the speed of light in vacuum, C, to the speed of light in a particle, that's Vp, velocity in a particle, is called, how is this called? All of you know, for sure. How is this ratio called? The ratio of the speed of light in vacuum to the speed of light in a particle. Yeah? Yeah. This is the, how did I write it here? Yeah, index of refraction. Index of refraction, and this is m, and m equals c divided by Vp. And if we are not in vacuum, then we have the velocity of the light in the medium divided by the velocity in the particle. So for example, if we are in water and we have a colloidal solution, then we would need the refractive index of water and of our particle at a velocity in both media, and this would give the refractive index. However, if we are in air, the velocity in air and vacuum are very, very comparable. So there we just keep it like this. So as long as we are in air, that's fine. We just need then this one for our particle material. It could be a droplet, so water when we talk about fog. It could be a solid. And of course, it has to do with the question if the material is conductive or not. This would make it much more complicated, because then it's how it's called? It has a, now I'm missing the word. How it's called in math when you have plus I. Yeah, imaginary part, right? Okay, thank you. Good. So, anything else for here? No. Okay, this is non-absorbing, but we will see this in a second. And then, I think all of you know this, but it's important to recap it for the lecture, and then we have to talk about something else, and this is polarization. So polarization of light. And polarization of light is quite interesting because we can say, okay, when the transverse oscillation of the electric light vector occur in all direction perpendicular to the direction of the propagation, the light is said to be unpolarized. So complicated sentence, but I like the two pictures here, and basically the sunlight is unpolarized, so the light from the sun has no polarization as long as it does not interact with the atmosphere. And this means that the photons in the wave has a Y and X component. And I really like the picture on the right to have the concept. So this is basically a drilling machine, and you have a rubber on the drilling machine, and so this means your rubber is going in circles, but also has a wave movement. And this is unpolarized. And then you put it through a polarized filter, and this is what you see on the on the left or on the right, and this is why I like the experiment really. So if you have the rubber going like this and you have the polarized filter, you will just polarize the movement. So after this interaction, the rubber only goes left and right. Okay, so you completely put out the other component. And this is what a polarization filter is doing, and this is what you see also on the left image. And I have one polarization filter with me because this is the concept sunglasses are using, so it looks completely different. And especially if I look at the sky looks completely different. And this is what you meant with brightness, because the polarization gives certain brightnesses, and sunglasses take these brightnesses out, which comes from polarization. Okay, this is why there is a polarization filter, and this is when you look through it in the sky, the color appears completely different and it appears less bright. And it's important when you are in the car, right? You don't want to you want to look clear. And there's also a quite interesting example from my time in the company. And there basically we tempered glass, so we made safety glass, so it has nothing to do with particles. And what happens is the glass is in a furnace, it's bent, and then you quench it very fast. Why the tempered glass is so strong, and what happens during the tempering? So this is what we call a blow box, and it's how it sees. So the glass is in between, you also can see it. And then you very fastly cool it down from 700 degrees to 400 degrees. And this gives these safety properties. What happens in the glass when you cool it down within 3 seconds? Yeah? Yeah, you increase the hardness, but why? The increasing hardness comes that window glass, if it's not safety glass, it's cooled down slowly and not so fast because this takes a lot of energy. But if you cool down the glass in 3-4 seconds, then it's harder. But why? Yeah?
I have a question. Is the glass melt glass? Or?
Yeah, it's not completely liquid, but it's mold.
Okay,
so you can bend it very slowly, okay? And that is why you increase the heat, you bend it, and then you have to decrease the heat very fast. But what happens in the glass to get it harder? Yeah, but here, yeah, you're completely right, but we don't talk about alloys, okay? Because there is no concentration gradient. It's always the same material. But what happens if you cool it up very fast? Exactly. So what happens is you cool down the outside very fast, but the inside is still hot. And this means the outside is compressed because you cool it down, while the inside is still warm. And this gives tension into the glass. So what you do is you freeze tension. And this freeze tension gives the strong properties to it. And to see these tensions, or to measure them, and this is, I mean, you can imagine, it's like a shower head, right? And this is what you see on car glasses. So this is a normal car glass. If you go out, if you look at my car or other cars, and if you now put on a sunglass with a polarization filter, and if you have sunglasses with these kind of filter, you can give it a try, this happens. And what happens is that you now see the pattern, and you see the pattern of the blow box, because this pattern leads to the fact that the tension in the glass are not completely everywhere the same, right? Because the air comes out like the water from a shower, and to see this, you use a polarization. So if you look at polarized light, you see this tension in the glass. So that's a quite nice measurement example of quality checks for tempered glass where we use polarization. Okay, if we go back now to particles in general, I would like, because this is something, I mean, I'm not an expert in light diffraction, but it's quite interesting to see that if you dive into the topic, and probably for you it's the same, you get a lot of words you already know, but they are not always cleaned up. So what for me is important that you generally can name the interactions of light with matter. And this is what you see here. So when we have aerosol particles, there are 5 things which can happen. And they are very often mixed up or not really precisely named, but they are different in what they are meaning. And the first thing is, so the light comes in and the wave, so it comes in and the light wave is just reflected. Okay, this is what happens in a mirror. So this is specular reflection. And this means that the incident angle and the outgoing angle are the same, exactly. This is reflection. And then we have the energy received can be re-radiated by the particle in the same wavelength in all directions, but with different intensities in different directions. And this is something else than reflection, and this is scattering of light. From Thomas Jüstel, you maybe also know Raman scattering in the lab, or maybe in the lecture he talks about it. And the Raman scattering means that the wavelength changes. Okay, then the wavelength changes for in and out. And with this difference of wavelength, you can say something about the material. But here, when we talk about aerosol scattering, the wavelength of the ingoing wave and the outgoing wave are the same, but for scattering, the direction changes and the intensity in each direction changes also. So then we can say about the speed and direction changes by going from one to another medium. Okay, this is what we have here, refractive index, and this is called refraction. And for refraction, you very often find also diffraction, but diffraction is something else. Okay, so refraction means the light is not 100% reflected, but it goes into the material. And then the speed changes, and it's quite interesting. I mean, we have extremely simple examples here. If I look at the wall, the light doesn't go through. And if I look at the window, the light goes through and I see what is behind. So the interaction with matter depends on the material. If the wavelength and the wavelengths here are fixed, the interaction just depends on the material. And then it could be that it goes through or not goes through. For infrared, it would be different. For infrared, I could see through the wall and through the glass. It's a different wavelength. But here, for our wavelengths, I cannot see through a wall, but I can see through a window. So then the radiant energy can be transformed into other forms of energy, such as heat, or for a chemical reaction, absorption. So the light is absorbed by the material. And this is extremely important for aerosols. We will talk about this. I will show you some nice examples about it. And the last one is the incoming wave can be bent around the particle. And this is now diffraction. So bend around means you have a particle and the light goes like this, okay? So it doesn't hit the particle, but it interacts in the way that it's bended. So in astronomy, it's of course a very big thing because we have a lot of masses, but this happens also with small particles. And these are the 5 basic things for this class you should keep in mind. So reflection, scattering, refraction, absorption, and diffraction. And in the class, we will take a little bit more look into these phenomena. And who knows, there's one basic equation which explains all of this. Who of you knows which, or is extremely important to understand these phenomena? Who of you knows which equation this could be? It's not Navier-Stokes this time. Yeah? No. Snell's law, yeah, Snell's law, but we need a more general one. Snell's law, yeah, but Snell's law is important when it comes to refraction, for example, right? So.
That was broad.
No, I don't know this equation, or I didn't understand. I have to look up then. And not easier, but more fundamental, yeah? No, it's not what I meant. It's, we will not touch it, it's right, but it's much more fun. Actually, I even don't know if you have this in the chemistry classes, maybe with Michael Bredol. Maxwell equations, okay? Whom of you had classes about the Maxwell equation? Okay, then I will shortly introduce them. So the Maxwell equation is basically the foundation, as it's written there, foundation of classical electromagnetism and optics. So he derived a set of differential equations. And these differential equations relate electro properties, or electrostatic, to magnetic fields. So we have 4 of them. And in the first one, you see, if you have a charge, you get an electric field. That's the statement of the first equation. So the density is the density of charges, then there is the permittivity of vacuum, and then the E is an electric field. So if we have charges, we get an electric field. That's the first one. The second one is magnetic field is 0. What does it mean? It means, and maybe you have it in mind, that the electric field goes away from the charges, right? But if you think about a magnetic field, the field lines are always closed. And this is the 0 here, okay? So the magnetic field is always a closed field. The third one relates the change of the magnetic field. So if you look at it now, B is changing over time, and this changing over time will give you a magnetic field, or a change in the magnetic field. And the other way around is that if the electric field, the magnetic field is changing, this will give you an electric field, and on the other way, if you have an electric field which is changing, you get a magnetic field. And these things you probably know are described by the set of these 4 equations by Maxwell. And on the right, you see this nice GIF, and the nice GIF basically tells you that you have an electric wave. The electric wave has a electric field, and when it's oscillating, it generates a magnetic field. And this magnetic field also has field lines. And this relation is described by the 4 sets. And since we are talking about electromagnetic, here is defined as visible electromagnetic radiation. So what we are discussing is very closely dependent on the Maxwell equation. The bad news is Maxwell equations are not so easy to solve. Even with a computer, you need some insights. I don't want you to solve the equations, but I want you to take away, okay, what are the Maxwell equations? There are 4 of them. What is the main meaning of these equations, and why are they related to optics? So here the picture is quite, how to say, I really like the picture for you to understand how it's going. So in the Maxwell equation, we always keep it simple. And this means we think about an incoming wave, and the incoming wave is a planar wave, okay? So as you see there, so it goes up and down, it oscillates, but it's just one plane. But as far as it hits a particle, it changes because it interacts with the particle. And now the wave, when we talk in terms of scattering, is going to a planar wave. So that the shape of the wave changes, and this is re-irradiated by the particle. Okay, so we have an incoming wave, which is planar, and then it hits a particle, interacts with the particle, and then you have a spherical wave with a point source, and the particle is the point source going out. So here, and this is now where I need the board again, is you already mentioned the extinction. And extinction means that you have aerosol particles and they are illuminated by a beam of light, and they scatter and absorb some of this light. The others we don't consider so far. So scattering and absorption is basically what we need to describe their interaction with light for aerosol particles. And basically exactly what you said for the smoke is happening, the extinction, because you said you cannot look through the smoke, or it's shaded a little bit. It's not as clear as the areas where, because exactly what you see on the picture is happening. And we can use this for measuring, and in this measuring device, it's important that the light beam is a straight line. And to describe this phenomena of extinction, so that we lose intensity in the light, we say the ratio of light intensity passing the aerosol I to that incident on that aerosol I0 can be written as, so we have the ratio, this means we have I divided by I0. So this is the intensity of light. The intensity of light is measured in watt per area, so watt per watt per square centimeter or watt per square meter. And this is the intensity going through. So this is the leftover. So from the smoke, it's not the one which the smoke captures, it's the light going through. So what do you see behind the smoke? There was a small plant or something. So, and this is described as a quite simple function, E, and then to the power minus sigma extinction L. That's it. So what is sigma extinction? Sigma extinction is the extinction coefficient. And this is the fractional loss in intensity per unit length. Okay, so for normalized length, this tells me how much of my light do I lose when I go with the light through my aerosol. And L, what is L? Yeah? Genau, right, the length. The length, of course, has an influence, right? So if it's a very small area where I have my smoke or a very big area where I have my smoke, I lose more and more light. And this means this extinction coefficient has the unit of meter to the power -1 because this has to be dimensionless here, right? To have here dimensionless. So now the question is, what is the extinction coefficient? And the extinction coefficient is a function of the number of particles, n as the number of particles, the area, the cross-sectional area of the particle, because of course if the particle is here and the light goes through this area is important, how much light is captured, and then another value, and this is the value you also see in the slide, and this is Q extinction, and Q extinction is said to be the extinction produced by a particle is a function of the particle extinction efficiency QXT. So this is something similar like in a filter. Last week we talked about filters, right? And we had filter efficiency for the fibers. You can think here about something similar. Like the filter has, the fiber has an efficiency how to catch the particles. And this depends on different phenomena, diffusion, impaction, interception, and so on. And this is a very simple measure here, the particle extinction efficiency. So if we take a look here, we just can rewrite the equation a little bit because we know what is the area, and then we would have n dp square pi q extinction divided by 4. So now we have the size of the particle directly in there. And do I? No, I go here to this one. And the particle extinction efficiency Qx is similar as we discussed for the fibers, is the sum of Qx Q absorption plus Q scattering. Okay? So if the light goes in and interacts with the aerosols, there is absorption and there is scattering. That's a very simple one, and if we have it, I mean, there will be happen more, we will talk about this. But this is how the extinction efficiency is summed up. So what we need is these values or this value, and if we have the value, the size, we can calculate how much light we will lose through cigarette smoke or something else. And another one you will need is the so-called, where's my here? The size parameter, and there is scattering depends also on the ratio of particle size to the wavelength described by the size parameter alpha Actually, I got a lot of critics for my boards, and I try to work on this. I hope now it's at least a little bit more structure in what I'm writing here. And alpha equals twice dp divided by lambda. So this is the size, this is the wavelength. And I will give you an example, and then I hope you get an idea of the using of these the usefulness of these equations. So basically what we can say is that all aerosols scatter light, all of them. But not all of them absorb light. Okay, so we have some simplification for non-absorbing, or it gets more complicated with absorbing. And it's also important to realize that when the sun goes down, you can look into the sun, right? This is because of extinction, because you lose intensity in the light. You couldn't look into the sun if the atmosphere would not extinct light of it via aerosols. Just another explanation. So if we have this Q value here, or here, if this value is 1, it means the particle takes exactly the amount of light as the size it has, the area it has. Okay, so this is the meaning of this extinction efficiency. So if I have a particle size which is 1 and an extinction efficiency of 1, it would take 1 out of the intensity. The extinction efficiency can be larger than 1. And this means a particle takes out more light than just its cross-sectional area. So this means that if I have a particle here, like this, and light goes in, it not only takes out this amount of light, it takes out more light. If the extinction efficiency is 2, it takes double the light it has in area. So it means also if I have these 3 arrows here, and then I would have 1 here, 1 here, 1 here, 1 here, roughly, okay? So this is the amount of light extinct by the particle because it has an extinction coefficient, extinction efficiency larger than 1. If it's smaller than 1, it means that all of the light goes in, but less light is taken by the particle than its area, because it's maybe like the window, right? The window does not take all the light because light goes through the material. And all of these things are in the extinction efficiency, a little bit similar to filtering. So there are ways to calculate the extinction efficiency, and for very small particles, so nanometer, it's easy to calculate, and for large particles, we will talk in a minute what happens for large particles. But I don't give you the equations because I just want you to deal with the concept. And for, let's say, relevant size range, when we talk about aerosols, this extinction efficiency can taken out of these diagrams. So you have a diagram, and the diagram shows the efficiency on the y-axis and the size parameter, so we need this. So we need an information about the size and the wavelength. And then we can take a look, okay, what is my refractive index? Because it changes with refractive index. And if we have, for example, air and water droplets, do you know the refractive index of water? Yeah, say it. 1.4? Yeah, 1.33. So the refractive index of water is 1.33. So it means we have air and water droplets in the air. And then we can take a look here. This is air, this is water droplets, so this will not change. So the refractive index for air we have to look is 1.33. And then you already see that even here it's quite complicated because the function oscillates. And you have to really look for your size parameter at your system, at the correct refractive index, and then you can get or read out the extinction efficiency. And if you have this value and you know the size, you can calculate the loss of light through an aerosol. So it's quite easy. You calculate the size parameter, then you look in the diagram, and then you can do the calculation. In the diagram, you can read out that it's calculated for one specific case. What is the case here we are looking at? What is the case? You see it on the bottom of the diagram. Keep it in mind, yeah? Yeah, spherical particles, and basically we could discuss about the influence of the shape, but we will not do this. But there is another one given, yeah?
The light used?
Yeah, which light is used? Yeah, which one? You just have to read it. You have the information. Yeah? Yeah, then if it's written, then tell me. Exactly. So this is calculated for one wavelength in the visible spectrum, so for 500 nanometers. This will change for each wavelength. This is important to understand. This is wavelength dependent. So then we have something called extinction paradox. And the extinction paradox is that if the particles get larger, Q will be 2. And this is also what you see in the diagram, that if alpha increases, the line goes towards 2, okay? So this means for large particle, they take out twice the light their size they have. How does this work? This is called the extinction paradox. And the extinction paradox you see here, the extinction paradox means anyway, I think we still have problems with the audio, but we will see it afterwards. The extinction paradox means it takes out twice the light as its size, and this has to do now with diffraction, because the light around the body is diffracted, and you see it in the image there. And if you are very far away, the diffracted light doesn't reach you, exactly as you see there. So the question is, what is the distance? Because you see that there are 10 d squared divided by lambda. So this is the distance you have to have from the particle to get this effect. So if we talk about 500 nanometer particles, it would mean 500 square and then times 10 divided by 500, and this would mean that the distance is 5,000 nanometers. So if we have 500 nanometer particles somewhere, this effect will happen if I'm 5,000 nanometers away. That's not much. So I'm 5,000 nanometers away from the particles in the atmosphere. If you do the same for a cup of coffee, So if you want that a cup of coffee takes away the area twice its size, you have to be 200 kilometers away from the cup of coffee. Then this effect would happen. So for a cup of coffee, we will not observe this diffraction effect. But for small particles, it works very easily. So this is the extinction paradox for large particles. And then Qx is always 2. So now I would like to give you a very simple example, and I want you to calculate the example. And the example is seen here. So I want you to take a look at this and then write down what you need, because you need the diagram, and then I would like that you answer me the question here. So the question is, what is the fractional transmission of light through 10 kilometers of air? So what is the first thing you should calculate? Alpha, exactly. What is alpha? Alpha is very simple here. What is alpha?
In this case,
2? Oh, you're right. Sorry. You're right, because I was wondering. This is why I... But at the end it should... Let's see what changed. Because I was wondering about the 2. So what is alpha then? It will not change much at the end. The procedure will be the same. So what is alpha? Right, 3.14. Perfect. See? This is how easy we find errors. So what is the next one? What do we need to calculate? Or what do we do with the alpha?
we have to calculate sigma extinction.
Sigma extinction, exactly. So we need sigma extinction. And for sigma extinction,
We have the formula n multiplied by this.
right? So we have the formula, and this is n dp, and then we have pi qx divided by 4 times L. So we have everything, but what is missing? Yeah? Q extinction, and Q extinction we can read out now with the correct alpha value, and then you get a value of right? I would also say 2. 3.14, I don't find it, but I found the 3, and then we have a value of about 2. And if you put this into the equation, what is the equation we have to calculate finally at the end if we put all the numbers in? Which one?
I divided
Yeah. So what you have to calculate is I divided by I0 equals, and then all of this goes in there. Actually, this is not here because this is, the L is here. Did anybody of you made a calculation? No? Yeah, 0.68. So I would like to know the 0.99. Does it come from the alpha value of 2? Yeah? So with a different alpha value, you got a different Q extinction. So with 2, okay, you go 1.33, so you're below. Okay, and then you have 99%. Yeah, 96%. So here it's 0.68, and this means 68% of the light goes through the fog. And it's quite interesting that with the error I made, but then you have a quite, usable second example. So if alpha is lower, so you have alpha of 2, then you have a lower Qx, and this would mean that 96% of the light goes through because less of the light is blocked or scattered or diffracted or whatever. So here we can calculate how much light goes through the fog. And it's a little bit over-exaggerated, but it's seen there. So you have fog, and then if I switch out the light, so you have the fog, and you really see that on small distances you can see the trees, and the further away you see it really like layers, like you lose more and more information. So this is extremely dense fog, and this means that the concentration would be much higher than the one we have here, or the droplets are larger. So we will need still a little bit time because we started a little bit later, and I would like to go anyway a little bit more into some details, so I will not be able to, I try to finish till 12 o'clock and then we go into the lunch, okay? So the only thing we talked so far is about what can do light with matter and how we lose light by an aerosol. But what is the application of the Maxwell equation? So I also mentioned the Maxwell equation, but the important thing is that when you work with the Maxwell equation, you get certain solutions. And one of these solutions is a very simple one, and this is called Rayleigh scattering. Whom of you knows what is Rayleigh scattering? Do you have this in another class, Rayleigh scattering? Okay, so this is a very strongly simplification, the Rayleigh scattering. And what we are doing here is we are looking at particles which are compared to the wavelength small. So very small nanoparticles, 10 nanometer or something, or molecules. And the thing is, if you have these very small particles, the light wave comes in like this. And your particle is here. So it's much smaller than the wavelength. The wavelength, if you remember the GIF, creates an electric field. And this electric field, and this will be also important for adhesion later, creates a dipole in the molecule or in the nanoparticle. So it induces a dipole. This means the electrons in the particle, in the nanoparticle, are moved. And the movement of these electrons depends on the electric field, so it depends on the light wave. And since the light wave is oscillating, this dipole is moving, also oscillating. And this dipole also has an electric field and also radiates. So the light wave induces an oscillating dipole in the particle molecules. Incoming radiation is distributed in all directions by the molecule or particle. So why it's distributed in all directions? Because the wave is going up and down, so the dipole is moving in all kind of directions, so it radiates in all kind of direction. And this is why the pattern you get is this on the right-hand side, the image. Okay, so this is a small nanoparticle or a small molecule, and in this case, the shape is really not important. So a molecule is maybe not a sphere, but the shape is not strongly important here. And you see that, and this is what we had in the beginning, the scattering depends on the position. Okay, so if something scatters, it's different if I'm here or if I'm here. It could be that on a position I get more or less light. And you see now the scattering is the blue and I'm the light blue. I'm going on this circle around the blue, and this means sometimes I get more light and sometimes I get less light. And this is Rayleigh scattering. And for Rayleigh scattering, you see two very strong dependencies. So the equation, we don't have to talk about the equation in detail. It's the intensity here, similar like this one, depends on the incoming intensity, of course. R is the distance from the particle, so how far I am away from the particle. But there are two extreme strong dependencies. Which one? Yeah?
Refractive index and also the size of particle.
Yeah, refractive index is there, it's correct. But is it really strongly depending on the refractive index? Theta is my position, okay? But take a look, you said particle size. That's correct, it's to the power 6. That's a lot, okay? And this is what you saw also for the cigarette smoke. The cigarette particles get larger, they are not more, they get larger. And this is the influence of particle size. It's not always to the power 6, for Mie scattering it's to the power square, but the larger the particle, the more it scatters. So what else, which dependency is also very strong? Yeah? The direction is okay, there's a much stronger one than the direction. The direction is correct and we see it in the diagram, but there's a much stronger one than the direction, yeah?
Wavelength.
Yeah, the wavelength is to the power 4. So the scattering extremely depends on the wavelength. So do I have more scattering for large wavelengths or for low wavelengths? Low wavelengths means I have more scattering. So now you can explain me why the sky is blue. We have the visible light. Where is blue? Here or here? Here, right? Is this scattered more or less? More. So this is why we see it. It's scattered. Okay. So you can calculate with this, or first I show you the explanation. So what you see here is the light goes in, and since we have the dependency of 1 divided by lambda 4, the blue light is much more scattered than the other colors. And this is why we see the blue light. I mean, a lot of light goes through anyway, but we see the blue light because the blue ones are scattered much, much stronger. So we can calculate the intensity of what I see there for all colors, but 1 divided by lambda to the power 4 tells me blue is scattered much more. And this is, also something I calculated here. So I generated a very simple Python code. And then you see that the intensity over wavelength for blue is extremely stronger than for red. And if you look, you find the diagram also much nicer in the internet. And this is why we see how the sky looks like. So my question now is, why is the sunset red? So if we go back to this image, why is the sunset red now? So that's me, okay? That's the atmosphere. And here is the sun. This is the picture. What happens if the sun goes down? Yeah? The angle changes, right? So the sun is now here. But it's not it has to do with the angle, but it's not the angle dependency in the equation. What changes, yeah? And with what is changing with distance, you don't see it so nicely here, is the path the light has to go through the atmosphere. Yeah. Okay. Think about the 10 kilometer in the fog. This changes. And what happens is that when the sun is here, the blue is scattered very nicely away everywhere, and I see this. But if the length increases, the blue is scattered somewhere away, and then it's gone. So there's no blue anymore. And then the other colors appear. So now the question comes, if you look at this picture, we will have a blue sky, and based on this explanation, we should go from blue to green to yellow to orange to red. Does anybody of you saw this in the sunset? That the sky starts with blue and then we get green, we get yellow, and then we get a red sky. Is this what you see every day? Yes? You see this every day? No, no green, right? I never saw green. Me too. So what happens with the green? And there now absorption comes into play. So there is something called Chapuis absorption, and Chapuis absorption is what we had here on, let me see, where is this slide? Somewhere here. Yeah. The radiant energy can be transformed into other forms of energy, such as heat or for a chemical reaction. And this is in the Chapuis absorption happening with ozone. So ozone is dissociated by the waves, by the light. And this is why we don't have green and yellow. So, which slide I was? Somewhere here? No. Yeah, here. So it means the blue at the beginning is scattering, and then we have blue all the night till the sunset because Chapuis absorption comes in, and this kind of takes care that we don't see green and yellow. And at one point, just the red goes through, and then we see a red sunset. So it's quite remarkable what happens there. And this is Rayleigh scattering, and this works for very small aerosol particles, and this works for molecules as we have them also. If we go to a little bit larger one, it gets more complicated, because for a larger one, we have to talk about Mie theory. And Rayleigh scattering is a very simple case of Mie theory. For Mie theory, and this is what you see here, there was this guy, Gustav Mie, and he basically solved the Maxwell equation for the case of a spherical particle, and then the light goes in. It's not very nicely. So for this case, he solved the Maxwell equation. And it's one of the solutions which is completely analytically correct. So different to the Navier-Stokes equation, which we cannot solve analytically, Gustav Mie found a solution for the Maxwell equation for a sphere, how the light interacts with and around the sphere based on the four equation. And this is, in a very special case, the Rayleigh, the intensity, this is what comes out. And if you take a look at the paper, I mean, it's a German paper, but you will find also an English translation, and this paper has 60 pages, which is a lot for a paper, as you know now, and most of the pages look like the very right one. So it's a lot of calculation, and in the past, when we didn't have powerful computer, it was quite a problem because the solution was there, but to calculate intensity, depending on a refractive index, depending on the angle, and on the wavelength, takes months, okay, because you have to do all these calculations by your hand. And you just want to figure out on which position you get how much light for your given system, and this really takes months, but the computer nowadays gives a lot of useful help, and the equation itself is not so complicated. What is more complicated is I1 and I2, and this is this Mie intensity parameter, because if you look at the equation, it's even simpler than the Rayleigh scattering. There is just now a dependency of the wavelength to the power 2, and now the dependency changes not only in the exponent, but also the wavelength is not anymore on the denominator. Is it the denominator, the one below? I don't know. Yeah, it's the denominator. 50-50, good. This changes a little bit, and the Maxwell, the Mie theory is the explanation why the smoke of the cigarette is white. Because all colors are more or less refracted, scattered in the same amount. And Rayleigh scattering happens for the cigarette particles because they are very small, and Mie scattering is for the what comes out, because what comes out is the cigarette smoke goes in, we have a high humidity, 95%, and then the particles are in nuclei for water droplets. So what comes out is larger water droplets, and they give you white light, not the blue one. Now, basically, also you have to calculate with Mie scattering for to be very correct for the cigarette smoke, but the effect at the end is the same as we see it in the air. So you see now something changed for Mie scattering. The pattern changes compared to Rayleigh scattering, and it gets more complicated the larger the particle is. So it's really a different phenomena than Rayleigh scattering. And what you basically need are these Mie intensity parameter, and you can look them up. Here is the Mie intensity parameters 1 and 2. They are calculated for 2 different angles over size. And now you see the problem. The left, these straight lines you see, this is 1 divided to the power 6. This is Rayleigh. But once at a certain size parameter, you see this oscillation coming in. And this is Mie scattering, and this is the pattern of the scattering looks completely different now. So with these, if you have these parameters, you could put them there. You can make the calculation. And here, this is a very important diagram because we have 2 systems here: latex particles and a dye. And one of them is absorbing, the other one is transparent, and you see the calculated values and the measurement. So this is experiment, 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 and this line here is calculation, and here it's the same. The dashed line is calculation, and here are the experiments. So the theory works very, very well with the experiment, and what is important, the left part goes with d to the power 6, and this is Rayleigh. It's very easy, it's a straight line. Then the complicated part comes, this is the Mie theory, then you really have to go in complicated calculation because the scattering pattern looks really, really complicated. And then when you go even larger, we have this extinction paradoxon, and this is basically what we call geometric optics, and then you have a straight line with d to the power square. So it's again a simple area. I would like to go into another example, and this is again aerosols in the air, and this is the eruption of the Tambora, and this is from 5th of April of 1815, and this is quite well documented because at this time the British people had their colonies there, and they wrote a lot of what happens there, and it is reported that when the volcano eruption started, they thought there was an attack going on because it sounds like cannons. And they were really alert. And then what you see here is how the volcano erupts aerosol particles. And these circles show you how fast they are traveling. So now we can think about the Sahara sand again. And basically here on the diagram you see a depiction, and the depiction is the thickness of the settled particles away from the volcano. So it's quite vice versa. The farther you away, the less thick is the layer of particles which rains down. And the interesting thing is now, what are these aerosols doing in the environment? And this is why it's so interesting here, because this is a really remarkable eruption of a volcano, so extremely strong. And it's quite well documented because during this time there happens what's called the year without summer. So this is a local event somewhere in, I think it was Indonesia when I was, right? But this local event leads to a change of the global temperature decreased from 0.4 to 0.7 in average. So a volcano eruption on one point can lead to a year without summer. So the summer temperature were the coldest between the year 1766 and 2000. So only when now, since 2000, we really see the impact of climate change, and these numbers are going crazy. This was a remarkable impact of the aerosols are just going into the atmosphere. So the results are a major food shortage in the northern hemisphere. This happens in the southern hemisphere, but in the northern hemisphere, there was no summer, so no food. So there was really a big problem. And what you see here is the anomaly of the summer temperature. And you see that in Europe, it was really, really cold. So less than 3 degrees in summer than normal. And this is not good for crop and so on. So if you at this time, of course, all the farmers and everything is very sensitive to the climate, right? They need very stable conditions. And the change in temperature leads to a fail in harvests, right? So it's too cold to get the amount of food you normally get. Between 1816 and 1819, there was a major typhus endemic's occurred, which is also related indirectly to this change in the climate. So they also had issues with this, and huge storms and abnormal rainfalls with flooding of major rivers are attributed to these events. So we really see the impact of aerosols, and it was recorded as the 3rd coldest summer so far we had. And this is just a local event. So we see here how sensitive this can be. And the situation in the US, so quite far away, severe frost occurs every month. June 7th and 8th, snowfall. Okay, so there is no snowfall in the US normally in June. And yeah, of course, thoroughly frozen that it never ripened and was scarcely worth harvesting. So there's also nice statistic, and this is when you look at the amount of animals. It's in German, but basically what you see is the amount of animals, and you see that this number really decreased. So horses, pigs, and so on, and you have before the eruption, these are the numbers before, and then you see like how all of them really died. Here for them it's fine, but so it has an impact for the farmers, for the people, and again, this is a very nice example how aerosols affect climate and how this affects the society. So this is, I meant a little bit oversimplified, but it's, in my opinion, a very important and nice example of the impact of aerosols. And this is why the boundary is so important, right? And basically the idea to determine the boundary is to use this value here. Okay, this is an idea to set this parameter here as a threshold limit. Okay, which one I don't know, but it's the idea to take the optical or the extinction basically as a measure of aerosol concentration to avoid these ones. So I still have some examples, and I really want to go through with them. Who knows from whom is this picture? Who of you have seen the James Bond movies with Daniel Craig? Yeah? Then there is a situation where he, I don't know if it's this image, I think it's this image. He met the new M. M is the guy who always make these gadget for him, right? And the new M is a very young guy. And do you know where they met or meet? Okay. They meet in the art gallery in London, and I think it's in front of this image, picture. So it's there. It's called Fighting Timorine, and it's a very important image because it's an old ship, and then you see a new ship, like a steamship, and it's kind of sad. Okay, how the world changes due to technology. So the old generation of ships, which are sailing ships, are now put out of order, and the new generation of steamships, and it's very generally seen about these change in technology, and there is kind of a very romantic story about the old ship and whatever. What else do you see on this image? Yeah, the sunset. And the image is made by William Turner. Whom of you have heard about William Turner? Yeah? Who is William Turner? Not the one from Fluch der Karibik, not this one. No, this is a real picture in the art gallery. The other guy from, what is Fluch der Karibik in English? Sorry? Pirates of the Caribbean, right? That's the English one. Yeah, yeah. That's not the William Turner I'm referring to. He's an artist, and he's one of the major artists in England, or was, of course. So it's a name you should really know. And he made these kind of images, and he also made a lot of images from landscapes. So he made a lot of images from sunsets. And you can do research on these images, because the problem is the measurement systems we have nowadays, we don't have them 200 years ago. So it's not so easy to understand the climate. I mean, you can drill and get these ice, whatever you take out there, but paintings is a very useful tool. The problem is painters are weird guys. And this means you cannot rely on the colors, right? Because they maybe have a very special idea how to make it. But you can do the same as you do in a measurement system. The first thing you do in your measurement system, what is the first thing you always do? Yeah? Calibration, exactly. So if a painter just makes a picture of a sunset, I cannot do anything. But if a guy like Turner makes hundreds of paintings, I get an idea. So it's like a calibration. So here we see how he made the sky before non-volcanic sunset. And then we can look a few years later, and then we see that the sunset looks different. And this is related to, again, an eruption. Eruption of the Babuyan, 1831. The painting is from 1833. If you remember back, you calculated the time particles from a volcano fall down, right? Did you remember the time it took? I think in the exercise you had the time given and calculated the size, but did you remember for this, yeah? 15 years? Months, right? 15 months. Now we take a look, 1831, 1833. That's already a good one. So it means that on painters like him, we really can see if these events happen, which kind of impact they have in different areas of the world. And what you can do is if you have the calibration with the old ones and you have more than one, because you have to understand how the painter draws, but then you can make a Python code or whatever, and you can calculate red to green ratios, and from the red to green ratios, you can get an information about the aerosol concentration, because aerosols scatter in the same way. And this means if the air is very polluted, the sunset will be more clear? Red, right? It will be much, much more red, because if we have a lot of very small particles, this effect is strengthened. So if we see a very nice red sunset, probably a lot of aerosol particles are in here. These are devices, I will just go very fast through it. These are devices which we are using. And so all this theory is used to measure particle sizes, because it's extremely reliable and the theory is understood and work. The measurement technique is extremely simple. It works, it goes very fast, experiment is easy, and so on. You get a very, very good information about your size distribution, and this is why we like so much to use these kind of optical particle counters, or as you see here, light scattering detectors. So you can work with extinction, you can work with scattering, and there's also a project which is not it doesn't exist anymore, but I really like the idea. The idea was that you can buy something for your mobile phone, you put it on the mobile phone, and then you make a flash, and the flash will give reaction, right? Reflection, scattering, and so on, and then the mobile phone can tell you something about the aerosol concentration. And the idea was to calculate all this data, upload it somewhere, but so far they don't do it anymore. But the idea is really cool, because you just need something from a 3D printing machine, put it there, and then you directly can measure with the flash of your phone aerosol concentrations. I will go very fast. No, I will skip this due to time. We can talk on another point about it. But now I would like at least to go through a few last examples. So you know now why the sky is blue, but why are the clouds white? Yeah? Yeah. And what do they do? It's correct. So it's large water droplets. And what do they do? They scatter light. Which one? Which wavelength? The smaller ones. All of them, right? White is all of them. So here we see white clouds because the light is scattered by the larger water droplets and all of the light. These are not white clouds. These are rainy or thunder clouds. Why they are not white? Yeah? No. No. It's a good explanation, but they don't absorb the light. They scatter the light as the white one. But what changes? Yeah. And what happens if the concentration changes? Yeah, very good. So the concentration changes, so you have much, much, much more droplets, and the light cannot escape. If you get these very dark colors, these very expensive dark 99.99%, they use the effect of a labyrinth. The light cannot escape, okay? And this is, so they don't absorb, they scatter and they scatter. The concentration changes, the light here cannot escape, and here we very nicely see a white one. So this is volcano ash or carbon black. Why this is black? No. Now you can explain me why this, the ash is black, or why carbon black is black. It's not blue, it's not white, but why it's black? The question, why it's black? Yeah, so you see, so here you see black, right? So here you see white because of scattering, and here you see black because of scattering. Why do you see here black? Yeah? Yeah. So here now we have absorption. So the aerosol particles here, carbon black is black because of absorption. It absorbs the light, so no light is scattered, no light is reflected, it's black. So the mechanism between here and here is a complete different. So here we have scattering, here we have absorption. This is a sunset on the Mars. It's bluish. Why the sunset on Mars is blue? Not red. Yeah, yeah, it is very. The atmosphere is different, and in which way it's different? Yeah, I think there's no water vapor there. But yeah, you're right. There is atmosphere, but very low. I think 100 or 1,000 times lower than the air. There are a lot of dust particles in the air. Very small, very, very small. So we have a lot of Rayleigh scattering. But since the atmosphere is much thinner, we will see this effect on this angle. Okay. So instead of a red sunset on Mars, we have a blue sunset because of the thinner atmosphere and the a lot of very small dust particles. What happens here? Yeah? Yeah. Is it a statement or a question?
I'm asking the question, is there like visible sky?
So as far as I know, is normally everything appears red because of the high concentration of iron oxide, I think. So, and this is also why the planet is red, and then you see all the dust around and you see red. I don't know exactly about the impact, but I know if it's this case, maybe I find some images on NASA, but the case is that if the sun goes down, then you now have a kind of visible atmosphere because the distance is so long, but the concentration is so low. So then you have an impact of the atmosphere. On normal day, it should be red because of the material, but I don't know how the atmosphere, I would guess you don't see really atmosphere on the day. You just see the color from the surrounding. Maybe you can figure out. What is the atmosphere looking on a day on Mars? Okay, what happens here? It's a rainbow, by the way. Yeah? Mm-hmm. Mm-hmm. So it's scattered, reflected. It acts as a prism, so what do we have here? What is the mechanism? Yeah? Is it diffraction? You said it acts as a prism. And the prism means that the light goes in and travels with different velocities through the material. The different velocity comes from the different wavelength. What is this? Reflection, diffraction, one after the other. Reflection, right? So it's reflection what we have here. Of course, we have a little bit scattering and so on, but the rainbow we see because of reflection, not because of diffraction, not because of reflection, it's refraction. Because we have the droplet, the light goes in, it travels in different velocities, and then it bounces back, it goes out. And this is why you also see, you don't see it here, you also see, and I really highlight, there are lectures from Walter Lewin on YouTube about rainbows, and this is a really amazing lecture. And this is the explanation, you see a second rainbow also. And the color of the rainbow, the second one is tilted. So if you take a look, you go from the inner to the outer, it's blue to red, and for the other one, it's the other way around. It's red to blue. And you also see that in the rainbow, it's very bright, and outside the rainbow, it's not very bright. And all of this is due to the refraction. So it's darker. If you look for these, if you look at a real rainbow, or if you look at other pictures, you see that the outside is always darker than the inside, and it's not so nice to see here, but really observable, and this is refraction. So all these phenomena you know are very important, but I hope you look now a little bit different at them, and that's really important that you know these different explanations for the phenomena. And now the last question is, I mean, we already solved it, but again, because we always come back to this image, smoking is the perfect explanation of what we discussed today. With smoking, we can explain all the calculations we made here, right? With the extinction, we can understand now why smoke is blue and the other smoke is white. And if you observe a smoker, take a look at the cigarette and the bluish part, and from the mouth, it's white. And we also can explain why the transmission is different here from the white one to the blue one. And with this, I think we can end the lecture. I'm sorry that we took a little bit over time, so we shortened the seminar. That's not a thing, but I really want to make the points here because I think it's important knowledge for aerosol technology. And I hope the takeaway for you is that you have now an idea, okay, how does particles interact with light, and you can give these examples and tell me, okay, The volcano ash is black because absorption. And the thunderstorm cloud is black because of scattering, and so on. We talked a lot about aerosols in the atmosphere. I hope you really understand this is a big topic. It's an important topic, and it's not by luck that it's one of the planetary boundaries. And very shortly, not too much we talked about the optical measurement techniques, but I think you have lab class where you use them. And if you have these lab class, please think about this lecture. So then thank you for your extra time. We will make now a lunch break, and then we will back in half an hour here for the seminar.